Today I'm going to talk about weak bases. So weak bases can be neutral or negatively charged because they have to function as proton acceptors. So here I just have a generic weak base, A- in aqueous solution. And when it interacts with water, it functions as a proton acceptor to become HA. So HA is the conjugate of A-. A- is the weak base. HA is its conjugate acid. Water donates the proton to A-, so on the other side of the reaction arrow, it becomes hydroxide, OH-. This occurs in equilibrium because for a weak base, this reaction goes forward only to a very small extent. The backwards reaction goes as well because this acid has some acidity driving the reaction in the backwards direction. For this reason, we can say that the conjugate of a weak base is a weak acid. And we can also say the opposite, that the conjugate of a weak acid is a weak base. So weak are the conjugate pairs. Now, in your book, a lot of the weak base examples that you will see are amine bases. Amines are nitrogen-containing compounds, and amine bases are common weak base examples that you're going to see a lot in your textbook and in the problems on the OWL system. So ammonia is an example of the simplest amine, NH3. Remember that nitrogen forms 4 strong covalent bonds and it has a lone pair on it. Now, if we replace one of the hydrogens with a carbon, we can make a whole different array of different amine bases. So, for example, if we have CH3NH2, that would be methylamine. It's like ammonia, except we're just replacing one of the hydrogens with a carbon and this CH3 group here. You can also have ethylamine, where you're replacing the methyl here with this ethyl group, which is just a 2-carbon group. So the reason why these make good bases is because the nitrogen has a juicy lone pair on it, which is eager to accept a proton. So this makes these amine compounds fantastic weak bases because they are great proton acceptors. So let's do an example where we calculate the pH of a 0.5 molar ethylamine solution. So ethylamine has this structure here, and I'm going to remind you guys that it has a lone pair on that nitrogen there. The Kb of ethylamine is given as 5.6 times 10 to the minus 4. So the first thing you want to do whenever you do a problem like this is to write the reaction for what happens when the base reacts with water. This is a classic base hydrolysis reaction. The base is breaking water in the reaction. And what's happening is water is functioning as the acid. So it's donating a proton to the base to make the conjugate acid, which in this case is ethyl ammonium ion with a positive charge on it. Water's conjugate base is hydroxide, OH-. So that's what's left once water loses its proton. So this reaction is an equilibrium reaction because ethylamine is a weak base, so it has a Kb associated with it. We can write the expression for that Kb based on the equation of the reaction with the concentration of the products over the concentration of the reactant ethylamine, and that's equal to the Kb that they gave us in the problem. Now, I wrote that reaction again, and I want to create an ice chart underneath it so we can see what happens as we go from initial conditions to equilibrium conditions. So the problem gave us 0.5 molar as the initial concentration of ethylamine. So we fill that in for the initial concentration in the ice chart. We have no products to start out with. Now we're going to have some dissociation of that 0.5 molar so that I get 0.5 minus X as the equilibrium concentration of ethylamine. Water we don't care about because it doesn't appear in K. The dissociation of ethylamine is going to be equal but opposite in sign to the appearance of the ethyl ammonium ion. So we get plus X for that and plus X as well for the OH- because we have equimolar concentrations of all 3 of these species. 0 plus X is X, 0 plus X is X, And if we take these values and plug them into our expression for Kb, we get x squared over 0.5 minus x in the denominator. Now, can we make the assumption that this is equal to x squared over 0.5? I want to assume that the dissociation, the minus x here, is negligible. I'm going to teach you here a way to check that. The rule of thumb is that if you can take the Kb and multiply it by 100, and that value is less than the initial concentration of the weak base, then you can assume that dissociation is negligible, so you can ignore the minus x. So for this compound, our Kb is 5.6 times 10 to the minus 4. 5.6 times 10 to the minus 4 times 100 is 5.6 times 10 to the minus 2, and that is below 0.5. So it's a legitimate assumption to say that this Kb is going to be approximately equal to x squared over 0.5. Now I know that that is equal to that, so it's very easy to solve for x. X is going to be the square root of that Kb times that initial concentration, and that's going to give me a molarity of 0.017 molar. Now, what is X? Always go back to your ice chart to figure out what X actually represents. So looking at my ice chart, X is the concentration of hydroxide. It's also the concentration of ethyl ammonium. But the important thing here, since I want to calculate the pH, is the fact that it's the concentration of hydroxide, because hydroxide is going to lead me down the road to the pH. Hydroxide is 0.017 molar. Taking the pOH of that, or the negative log of that, I get a value of 1.8 for the pOH. And I get the pH by subtracting the pOH from 14. The pH of the solution is therefore 12.2. And this makes sense because this is a weak base. So it better have a basic pH well above 7, which it does. So that is how you calculate the pH of a weak base solution. I want now just to talk briefly about species that are non-acids and non-bases. We've spoken about this in the past, but I want to emphasize now that the definition of a non-acid is really anything that's a conjugate of a strong base. The definition of a non-base is anything that's a conjugate of a strong acid. Let me give you as an example chloride, or Cl-. Imagine Cl- reacting with water. Well, if it's functioning as a base, it would have to function as a proton acceptor to give HCl and leave hydroxide. But there's no way that is ever going to happen because we know that HCl is a strong acid. So if anything, this is going to be driven in the opposite direction. So chloride, Cl- is an example of a non-base because it's the conjugate of a strong acid. It's not going to accept protons to any great degree. So you can identify a non-acid or a non-base as anything that's a conjugate of a strong base or a strong acid. Okay, I just want to summarize this information really quickly in a table of acid and base strengths. So I've handwritten this table out. And this table gives you a number of things. So reactant, or what's on the left side of the reaction, and product, or what's on the right side of the reaction. I'm giving you columns with the Ka, the acid-base pair, and the Kb, which is the K associated with the hydrolysis of water by the base. I've listed the strong acids here in decreasing strength, Hi, HBr, HCl, HNO3, and H2SO4. For all of these, their Ka is huge. I can write their conjugate bases just by peeling off one proton to make I-, Br-, Cl-, NO3-, and HSO4-. All I did to write these was peel off a proton of the acid. Now, the stronger the acid, the weaker its conjugate base. So if I have a large Ka, I'm going to have a teeny tiny Kb for the conjugate base. And that teeny tiny Kb effectively means that these are non-bases. They are not able to hydrolyze water. By comparison, if we look at hydronium actually has a Ka. It has a Ka of 1. in its donation of a proton to make water. Now, water, of course, has an autoionization constant, Kw, of 1 times 10 to the minus 14, so that's a pretty small number. We can consider that as a non-base as well. As we go down in Kas, we get to the weak acid. So anything with a numerical Ka really is a weak acid. And here I've listed a couple of weak acids. There are thousands upon thousands of weak acids, but here's just a few of them in descending order of strength. So HF is the strongest. Remember that the larger the Ka, the stronger the acid. So as we go from this Ka down to this Ka, this is a really teeny tiny number for HCN. So this is a pretty weak acid. Peeling off the protons, I get their conjugate bases. So HF has F minus as its conjugate base. Acetic acid has acetate as its conjugate base, etc. One interesting thing is that I can always get a Kb from the Ka through this very important relationship here. The product of Ka and Kb is the ion product constant for water, Kw, which we know is 1 times 10 to the minus 4. This is extremely useful because if you have a Ka, you always have the Kb of its conjugate base and vice versa. So using this equation, I can calculate the Kb's for all of these bases. Notice that the larger the Ka, the smaller the Kb. This has a pretty small Ka, but a larger Kb. So the stronger the acid, the weaker the conjugate base. The stronger the base, the weaker the conjugate acid. Finally, looking at non-acids, I'm just using water as an example here. Water has the K associated with it of 1 times 10 to the minus 14. Its conjugate base, hydroxide, of course, has a K of 1. Hydroxide is a strong base. The conjugate of a strong base is a non-acid. So this is my nice little table. And to supplement that table on Blackboard, I have posted this sheet. So you can access this as a PDF on Blackboard. And this is showing much the same thing, the relative strengths of acids in aqueous solution at 25 degrees Celsius. So this is a list of acids decreasing in acid strength. So the strongest acid is here, and as we go down, we get weaker and weaker. These are the conjugate bases. This is the weakest base, and as we go down, we get stronger and stronger until we get to hydroxide, which is the strongest base here. And here are the Ka values. So it's just similar to the table that I just gave you with a couple of different acid-base pairs on it. So I would like to end this lecture by giving you a summary of the equations for acid-base calculations that we have done so far in Chapter 13. You can also access this as a PDF on Blackboard, so I've posted it for you as a PDF, kind of like a handout. It's a summary of all the equations for acid-base calculations. So remember, we started with the strong acids, and the definition of a strong acid is something that's completely ionized in water. So this is not an equilibrium. The strong acid reacts with water, and it gives its proton to water to make hydronium and the conjugate base. This occurs completely so that at equilibrium, the hydrogen ion concentration is equal to whatever the initial concentration of the strong acid was. Okay, you have no strong acid left in solution. So it's very easy to figure out the pH of a strong acid if you have the initial concentration of it, because that gives you the proton concentration directly. We also talked about strong bases. Strong bases are also completely ionized in water. For example, this metal hydroxide breaks apart into metal cations and hydroxide, and the concentration of hydroxide is going to be equal to whatever the initial concentration of the strong base was. So if you have the concentration of that strong base, you can figure out the concentration of the hydroxide because this is not an equilibrium. You have no intact base molecules at equilibrium. Weak acids and weak bases are very different because they're incompletely ionized in water. The weak acid reacting with water to make hydronium and its conjugate base this reaction is in equilibrium. So these are my double-headed arrows I just represented with an equal sign. This reaction occurs only to a very small extent. So I have to do an ice chart to figure out what the pH is of a solution of a weak acid. And I can make a really useful assumption to simplify the math. For a weak acid, as long as 100 times Ka is less than the initial concentration of the acid, then I can make the assumption that minus X is negligible. And the consequence of that is that the proton concentration is going to be equal to the square root of the Ka times the initial concentration of the acid. So that's very cool because you don't have to use a quadratic equation unless your Ka is very high and or the initial concentration of the acid is very low. So weak bases, similar thing, they're incompletely ionized in water, so the weak base interacts with water to make HA plus OH minus, and this occurs only to a very small extent. You can do an ice chart to figure out the pH of a weak base and make the assumption that minus X is negligible as long as 100 times Kb is less than the initial concentration of the base. So from there, you figure out X, which for weak bases is going to be the hydroxide, is equal to the square root of the initial concentration of the base times Kb. And from there, you get POH and then pH. So I hope you enjoyed that lecture, and I will resume with one additional lecture to complete Chapter 13 after this one. Thank you very much.